My name is Ronan Kerriel, and I work at the Xilinx Research Labs, and I'm also the editor for the specification of the SYCL standard. I will present you some extensions that we have for the Xilinx FPGAs and for the Versal ACAP chip in the Tricycle open source implementation. The problem we have nowadays, when you want to program some application on a real platform, is that you have to address all the accelerators you have in your systems. And for example, on our Versal platform, we have several different CPUs. You have an FPGA, and inside the FPGA, you could also have some specific overlay architectures you would want to program with some, for example, microblaze CPU to program and things like that. But more interestingly, we have our coarse-grained reconfigurable architecture where you have an array of cores and each core has its own memory. So it's a complex stuff to program, and if you want to scale this at the data center or HPC level, it will become more and more complex to deal with OpenMP, MPI, and things like that. So we really need a programming model, but fortunately, the good news is that with modern C++ and specifically with SYCL DSL, we can probably address some aspects of this. And actually, since SYCL is a pure C++ DSL, probably we can reuse the same tricks we have in C++ to express in some C++ classes more and more DSL to express and to address our problems. For example, you can start with C++20 to program a normal machine, I would say, where you have an homogeneous single memory view, but then you can, in this application, use some C++ parallel leaves, such as Cocos, that will allow you to express more stuff in parallel and to control more things. And the Cocos implementation could use C++ SYCL, and to also control more detailed stuff, you can have an architecture libs written in C++ expressing a lot of details, and going down, you could have some domain libraries to, for example, control some machine learning operation or some software-defined radio for 5G, for example, some very specific operators. So probably it's possible to do all that stuff in C++. So that's what we try to do in Tricycle with some extensions. So let's start with some FPGA extensions. So the most common optimization we can do when we execute, for example, some loops on FPGAs is to use pipelining. So if you consider here a loop with three operations, so you read, compute, and write. If you execute it naively on the hardware, you will have some kind of sequential execution of your loop. But if you think about that on FPGA, you have a real implementation in hardware, or all these operations, they will be unused most of the time. So if you execute the loops in parallel, you can overlap all the different stages and to improve the throughput of your loop. So what we've done in Tricycle is to introduce this green line. So when you have in a kernel some loops, you can express the fact that you want the loop body to be executed in a pipeline way just by wrapping the body with this pipeline decorator, which is pure C++. So it's not an alien pragma or an attribute as it can be provided by some other tools. The fact that it's just pure C++ means that you can implement it in a very straightforward way. For example, pipeline here is just a generic lambda taking some code, and your pipeline operation just execute your code, but before it executes this specific intrinsics, where the syntax is not important here, but it's just a way to express to our backend that we want to use some pipelining here. And uh, so uh, since we want this code still be compatible with some other SYCL implementation or to run on the CPU when you do not have a real FPGA, then the intrinsic itself, when you have a real Tricycle device, is something not very important here. But most important is that when you are not in this Tricycle extension, then your intrinsic for spec pipeline is just an empty operation, so it does nothing. So it's still compatible with normal SYCL implementation. Another interesting thing with FPGA is that you can partition memory. Yeah, a common problem for parallel programming since the 70s is that when you execute things in parallel, you will have probably some conflicts on the memory in your system. But the good news is that in the FPGA world, everything is reconfigurable, even the memory architecture. For example, if you have a 1D array of 16 elements, instead of having only one memory to store this element, you could decide, for example, to have a cyclic partitioning to distribute all your 16 elements on 4 memory banks in a cyclic way or in a block way, or even go wild and have one memory per element of your array. Of course, it will require quite a lot more hardware, but the performance will be quite higher in some application. But the same way, we can express this also in pure C++ by just introducing some new data types, new arrays with some obviously some types, but also some, for example, some block size and some partition parameters. So you will have A that will be a partition array at the end. So it's directly in the C++ types. So it's a portable C++, and then because you can run this on normal CPUs or on some other accelerators that does not support this extension, because you can always provide some implementation which are equivalent to a stud array. And you can do some introspection on this if you want to do some complex metaprogramming, which is not possible to do if you use some more traditional approaches, which are, for example, using some pragmas in some tools, or to use attributes in, for example, like in the Xilinx OpenCL C implementation. So for example, in the case of the pragma, the pragma description is not directly attached to the declaration that makes the code harder to think about, and it's not compatible with template metaprogramming in most of the cases. But at the end, what is interesting is that with Tricycle, you can generate some code that will be ingested by our backend compilers and just generate some kernels for the Tricycle kernels, and it will automatically generate all the infrastructure to run them and to generate the bit stream that will describe the real FPGA layout for the real execution. For example, here our kernel is the yellow part on the picture. Recently, Intel published an open source SYCL extension, which are pipes. And that's interesting because it extends some FPGA abstraction for pipes. We have already, for example, in the Intel Altera channels or in the Xilinx HLS implementation as axis stream, but with some modern C++ flavor. So it simplifies what we have pushed in some deprecated SYCL implementation before. So the idea is to introduce a new data types that will represent some communication channels. So the pipe here will be a pipe of integers plus some name to identify the pipe. And then to use it, for example, from the FPGA, you create a queue for your FPGA, and you launch a single task on the FPGA. Here it's forever. You will write on your pipe something produced by some produce function, and you will you will create another task that will read data from the pipe to process them on the FPGA. So you can see basically in 3 lines or 4 lines, you can create some very simple data flow programs that will run on the FPGAs with 2 kernels, with a producer and a consumer. Even more interesting, you can have some specific pipes allowing you to address the real hardware on your system. For example, imagine you have somewhere from your vendor some hardware description describing some Ethernet pipes to read and write from your Ethernet NIC. So in the user application here, you can create a NIC pipe named sniffing using the platform Ethernet with so it will be used to transfer some data between the FPGA and the host, and the data will be Ethernet packet, and you can have up to 1,000 packets in flight. So the idea here is to use the FPGA to capture the Ethernet packet, to do some filtering, and to forward the interesting packets to the CPU where they will be further analyzed. So for this, you just launch on your FPGA queue a single task that will read forever some Ethernet packets, and will just filter them. And if it's an interesting Ethernet packet, it will forward it to the NIC pipe here. And the NIC pipe is actually used on the host side, so it's executed on the host because there is no queue involved. And on the host, you will just analyze what you read from the pipe. So it's very terse syntax, so, and since everything is static, you can generate some very efficient code from this. We've implemented this in Tricycle on CPU for now by using Boost Fiber's buffer channel. And what is nice is in C++20, we have this new concept of ranges that bring some similar data flow programming style. So which means that for some spatial architectures, we can probably implement all these stud ranges as this kind of pipe operation. Okay, I won't say more on the FPGA part, but now I will talk a little bit more about the ACAP extensions. So the ACAP is for our Versal adaptive compute acceleration platform. And in this platform, we have a coarse-grain reconfigurable arrays with an AI engine. So the architecture is you have a lot of cores with their own memories and some specific network on chip to interconnect everything, and you have also an FPGA on board interconnected to this CG array. That means that we need a framework to program everything in the at the same time in a single view, so in a single source approach. So that's why we have developed this ACAP++ DSL on top of SYCL. So the idea is just to extend the basic SYCL object by templating them with 2D coordinates. For example, so the platform, the devices are the kernels are recycled as it, but now the cores are represented by tiles and with some XY coordinates, and even the memory of the tiles are also expressed in the programming model also in a XY templated way. And you can also access to the switches to program them inside the tile to reconfigure your network as you want for your application. So how to program this? So the idea is to use a device like the SYCL-like devices to template them by some layout. For example, here for our VC1902 chip that will express the X and Y geometry and things like that. And so you can run, for example, some programs, and this program is as I said, a templated tile by XY. And here in our Hello World program, we just want to express our X and Y coordinates. So we can probably run this like that. So each tile is expressing its own coordinate, and it's run on my CPU in emulation mode on my laptop here. So you can see it runs on different stud thread in parallel, so you can see that you have some race condition, obviously, but that's normal because we run everything in parallel. And you should not write code like this, of course. Okay, to help debugging, we have some graphics libraries because it's very useful to use graphics for debugging. And it's a small GNOME GTK application. Under the hood, we also use the MDSpan proposal to represent arrays and tilings and things like that. So, for example, you can run simple program like this to represent all the pixel and the tiles. So how to program this? So the same program, so we had 2x3 tiles, so we can express arbitrary layout in our programming model. We can use some the graphics tool, and here we run a Mandelbrot program, but also with specific explicit memory content. So in our programming model, we can weave in by using metaprogramming the program part of the AI engine content with the memory part of the content. And you can express both the program and the memory part in our programming model by using some templated data types. The memory here is just a pixel plane, which is a small array, and it's actually the same for all the tiles. And for the Mandelbrot computation itself, so we use X and Y coordinates to change a little bit the computation, so to distribute the work on our tiles. And by using metaprogramming, we introduce some new member function to access to our own memory. So it's accessed by this tmem alias. So then in the code, when we access, for example, for the pixel jy in plane here through M, it will access actually this memory tile in a type-safe way. So that's interesting that if there is no for a given tile, these data types, you will have an error compilation and not a runtime error. Okay. More interesting is that for some serious applications, for example, you want to execute some HPC-like stuff such as PDE, and here we want to have a demo that uses a simple first-order differentiation scheme because it's easier to fit on one slide. And the interesting part, if you distribute the content by block, it only requires some direct for neighbor communication. And that's something, if you think about it, which is not possible to do on GPU without going through the global memory, because the architecture and the priming model is organized like that. That means that you have some high latency and you use a lot of energy for this. But for our AI engine, CGRA, it should be perfect because we have in the hardware a way to address to the memory of our neighbor, so it should provide low latency and low energy. So the application, the full application in the sequential way fit on one slide. So it's three 2D nested loops. And here we use this Fortran-esque syntax because we use MDSpan from the future ISO C++ to express our code. And we will focus on this yellow loopness, this yellow operation. So if we distribute, for example, W by block on our tiles, then when you want to access to WJ 1 plus 1, 1 plus 1 might be stored actually in the neighborhood memory. So that's why you have this problem of how to access to these elements that might be at your neighbor's memory. So either in your hardware, you can directly read them, but it might complex the loopness, or you could extend all, for example, here, the W with an overlapping zone or ghost zone, halo zone, or whatever. There are different names for that to take into account this and to prefetch them, the data, by using some DME hardware or something like that. Okay, perhaps you can just run the program to express a little bit what's happening here. So we have our domain distributed by tiles. So you can, in the graphics interface, so you can see all the tile coordinates. And you can run the demo here. It's on my laptop in CPU emulation mode, so it's quite fast enough. And so here I have some different depth in my shallow water, so I have a different speed. I've had in a few for fun, a few boundary condition here with some holes, so you can see the diffraction of the waves in the water happening here. So, well, I don't know how it renders on the video recording, which is only 4 frames per second, but I hope it will be smooth enough for you to see what's happening here. Anyway, so the idea, the problem is that so in each tile you need to communicate some data. So I will just show quickly how it can be done in our framework. So as seen previously, so you have this mem alias to access to your own memory, but we have also the mem up, mem right, mem left, and so on to access to all the neighbors' memories. And you have, for example, if you are not a module on the top of the array, then there is a neighbors up. So you can just access to these neighbor memories and to do some transfers, for example, writing some content and to write it into your above neighbors and so on. And we expose also some hardware features such as barriers between tiles to avoid data races in the various tiles. Okay. What is interesting in this pure C++ programming model is that since in SYCL you can always run everything on CPU in emulation mode, then it's very useful to debug directly on the host, and also if you do not have yet a device implementation running. So you can use a normal debugger, and this programming model on the host, one thread is run on stud thread, obviously, but each AI engine tile core or each GPU work item, FPGA work item runs in a stud thread on CPU, so you can debug this in GDB, which is scriptable in Python. You can use normal memory checkers such as Valgrind or Ubisan or whatever. And all these tools are also scriptable in Python. So you can really develop your own debugging tools to ease that. And what is amazing actually is that since we have a direct mapping from some hardware features into normal C++ stud thread plus logs plus condition variables and things like that, you can actually detect on the CPU some race condition related to some hardware features. So that's pretty cool. It would be impossible to debug this kind of code otherwise. Well, and you can use obviously a lot of classical C++ debug and use graphics things and so on. So to conclude, so obviously SYCL is a very interesting programming model providing some foundational base for modern single source heterogeneous computing. And that's important because you have to focus on the whole system, which means system-wide compute language like SYCL. And single source allows you to address the full application and enable generic libraries to address both the host part and the device part, because at the end, that's what you have to optimize in the real application. And now the heterogeneous platforms are really heterogeneous with a lot of wild accelerators. And Tricycle is used at Xilinx to develop and to experiment this DSL extension on top of SYCL for spatial computing for our Xilinx FPGAs or ACAP, coarse-grained reconfigurable arrays. And what is interesting is that we can express in very modern C++20 ways some explicit detail. I mean, you can have an explicit programming models that allow us to reach a bare metal efficiency. For example, we can provide some MD-span-based abstraction on top of DMAs or to express multi-level memory hierarchies or overlay architecture. So it's pretty neat. And since it's all a pure modern C++ DSL, well, you can directly emulate your target on CPU and to debug and even to co-design your application, your system, to experiment with some new architecture details that you have not implemented yet on the real hardware and to see how it would be easy or hard to program and how the performance would be. So it's cool to have this, to rely on this host device backend execution mode of SYCL just for this. That's it. If you have some questions, I think you can ask them online. Thank you for your time.